we're going to look at identifying this sensor. So there it is, amongst all my breakout leads is the air conditioning pressure switch, which is a LIN node, a LIN module. Got breakout leads on there. We've got the ground path, we've got the LIN signal, and then we've got the power supply to the sensor. Note also around the ground path that we've also got a current clamp, as that we know that this device will switch and pull down the voltage to near zero, so we can use that to our advantage. Everything's referenced to ground, so all three cables reference to ground, and here you'll notice that we've got a pressure tap, something we've had made up on the high pressure circuit, so we can actually read the physical value with the transducer, and then later on cross-reference it with the LIN data that we've got from the sensor itself. Here's our PicoScope capture then. So we've left the channel labels open, so we've got the data. LIN Bus will be on channel A. Channel B is the power supply to the switch. Channel C will be the ground, which is why we're on 50 millivolts. We just want to look at the ground level. And then we've got that current clamp around the air conditioning pressure switch ground wire with the arrow facing away from the switch, because we know that the switch needs to pull that down to ground. So we want the current traveling in a rising direction, so the arrow faces away from the sensor, away from the switch, sorry. All right, so let's turn on ignition. And there we have LIN Bus activity. Notice how the voltage crept up there because this is an electric vehicle, and that is DC-DC active. Just turn ignition off. So what can we derive from this at the moment? Well, there is our voltage drop on the ground line. Nothing too heavy to worry about there. At the moment, it's difficult to see if there's any sort of relevance in the current waveform, but let's increase the scaling. So actually the quickest way to do this, we'll have a tidy up. Let's get rid of channel C for now, and channel B doesn't really offer us anything, so we're just going to compare the LIN signal with current flow, and then we'll just scale up. There we are, just by increasing, rolling the mouse over the scale, and we see now that we have these spikes that may well relate to messaging from air conditioning switch. So let's zoom in. And we'll zoom in again. And we'll increase the scaling. Let's use the display here. We're up to 14, 18. It's quite a lot of increasing the amplitude on the scale. Nevertheless, it works really well in this scenario. And you'll notice here we talked about the header, didn't we? Header being the commander requesting, and then we are getting a response, so the current is flowing in a positive direction from what looks to be the air conditioning switch, the air conditioning pressure node. So how could we use that to our advantage? How could we find more evidence that that is relevant? Well, let's add the serial decoder. So serial decoding, LIN on channel A. Remember, we went for 6 volts and it was 3 volts hysteresis. Okay, board rate's been selected automatically. I happen to know that it is correct on this vehicle. We want hex in the display and hex in the table, and finish. And let's just have a look then here. Here we have our protected identifier, which comes from the master, the commander. And also hidden in there is the frame identifier. Now that is of real interest to us because the frame identifier carries information about the data within. And of course, in this scenario, the node responsible for that data. So let's see if we can now, well, we know that it is protected identifier 64, which means our frame identifier associated with that is 24. Let's add a filter. We will go for frame identifier contains the value 24. We'll now zoom out, and you'll see now in the decode table, not so much in the decode table, sorry, in the graph view, within the scope view, that only messages with the frame identifier 24 are displayed. Just zooming in on that right now. And at that point as well, notice how the current peaks also align with frame identifier 24. So we have it on reasonably good authority, I think, there, that we have proven that protected identifier 64 with the frame ID 24 is our air conditioning pressure switch. But can we go further? So using another option to try and identify or confirm that protected ID 64 and frame identifier 24 is actually the air conditioning pressure switch. Let's leave the filter in place and let's zoom out, and we'll actually disconnect the the pressure switch itself. So let's zoom out. We don't need to be this slow actually. We'll go on 200 millisecond divisions and we'll turn ignition back on again. And let's get LIN Bus active. And we see there that we've got ID 64 and 24 only. And when the filter is applied, you'll notice how the spikes in the current align. There they are. So I'm going to disconnect the air conditioning pressure switch midway through the capture, and we'll see what happens. I've just disconnected it, and notice there we've actually gone to red because now we are in error. We've actually switched off. Right, there we are. So if we look here, we see that we had messaging from the air conditioning pressure switch. Then I disconnected the power supply to it. Current stopped flowing from the switch, or through the switch I should say, and then everything was decoded in error. So let's just modify the decoder so that it only applies to the current buffer. And finish. So you'll see here at the start of the capture, we were black, and then as I've disconnected the power supply, we were in error. Okay. We'll do that once more, but I'll actually bring back, in fact, no, I won't have to, because if I bring back channel B, you'll see there at the precise point where I disconnected the voltage supply to the switch, how at that point we went from good messaging to no messaging. So I think we can safely say that frame ID 24 is from the air conditioning pressure switch. Okay, so with those two items in mind, so that's using the current clamp and then disconnecting the air conditioning switch as well, is there another way? Yes, there is. So let's run the scope first of all and reconnect the power supply. So hopefully we'll catch that in a buffer. There we are. And if we go back, we should see the point that we went from errors in our decoder to no errors because they're highlighted in red here. And in fact, let me get some separation on that. Yeah, highlighted in red there, and then highlighted in grey. So yep, all good. And also notice now the current is passing through the switch because it's now reconnected. So we talked about voltage signatures present in ECUs, and sent is a typical example because we know in a sent packet it consists of 2 ECUs. So here is where sent was actually transmitting. This is the air conditioning switch, and we know that the master is at the beginning there, and that there should be a slightly different ground level, yeah, right there in the response. So the response is the data section. Now, it's not very clear to see here. It's not so well defined. You may actually be mistaken for thinking that that was the master requesting a response from itself because the ground level looks to be the same. Maybe if we change the scaling and let's increase it, let's see if we can get some separation in the ground level. And I think we are seeing it there, aren't we? So let's grab this ruler. Yeah, let's keep going. We're up to 9, 10, 11, 12. Yeah, now we are seeing a different ground level during the response. We know that that's the response because that's where the current is passing through the air conditioning switch. So my thought here is to actually add some voltage drop into the ground line. So if we place a resistor in the earth for the air conditioning switch, this voltage drop here, which at the moment equates to very little, if I try and put that ruler at that point and have a look at the delta, 40 millivolts between the master, the commander, sorry, requesting, and then the response from the responder, which is the air conditioning switch. If I add a deliberate resistance value into the ground of that switch, the air conditioning switch, that voltage drop should increase, and we'll see a difference. We may even see errors. So what I'm going to do now is add 750 ohms of resistance in the ground wire to the air conditioning switch, and let's see what those results, or how those results pan out. So here we have added the resistor. So it's a wire wound resistor, a 750 ohm. You'll see that the green that comes from the pressure switch into our breakout cable, whereas it went originally into the connector here, will now go through this 4mm breakout, through the resistor, and back in to the harness connector. So basically we now have 750 ohms resistance in the ground line between the air conditioning switch and vehicle ground. All right, so now we have this 750 ohms placed in the ground of the AC switch. We need to make some adjustments to the software. So first things first, let's go to views and reset, because all our scaling was way out. We'll take away the rulers and we'll turn on ignition. There we go. There's LIN Bus. And you'll notice now that we've got multiple errors. Not surprising, because we've added such a high resistance in the ground that we can't pull that voltage down low enough to determine that a 0 or a 1, or to define a threshold which defines a 0 or a 1. So notice now that the current, well, let me just scale up on the current. We're not seeing those spikes. Not surprising, because there's no current flow, but also notice channel C. So let's bring channel C back. Channel C is overranged because we have now voltage drop. So let's start increasing the scaling on channel C, and we get to 2 volts. Let's have a look where we are. It's still overranged. Let's try 5. And we're still overranged. Okay. It's looking a little bit crowded here, so let's try and improve. So this I find very interesting. Let's take, no, let's not take away the current, because the current's important. But we'll pause when we've got a full screen and just look at that. So now where we had the spikes in the current when the resistance was good, now we've increased the resistance, we've got voltage drop present when the pressure switch tries to transmit. Let's have a look at what's happened to the voltage drop. Let's just zoom in on a couple of packets. Wow, I think that speaks volumes again, doesn't it? So there is the commander, there is the response, there now is voltage drop. So let's just scale up a little bit. Display. Okay, so voltage drop when the air conditioning switch tries to transmit, and we've gone from, I think it was 40 something millivolt drop to 5.4, a considerable amount, no current flow. Let's just bring the decoder back in, and also the decoder, the decoder in the graph view is there. Right, let's just jump to any packet at random. In fact, everything with frame ID 24 is red. Let's just double click on this one. It's taken us straight to packet 115, that is. Let's do that again. I just zoomed out a little bit too far there. So let's try the window zoom, marquee zoom. Okay, so all in all, let's just hover over that, just so that. There we are, packet 115, protected ID 64, frame identifier 24, now has excessive volt drop. I think beyond any doubt now, we have identified the frame ID and the protected identifier for the air conditioning pressure switch. We are now going to connect the BNC Plus pressure transducer to channel B. Okay, we can then apply the pressure transducer to our pressure tap here, then close the tap. We're sealed at this end, so there's no risk of gas leakage. Then what we'll be able to do is measure the physical pressure value and correlate that to the LIN data, and hopefully be able to identify what the packets mean in the data field, and also convert those into human readable data. Okay, with our transducer connected, we now need to make some modifications to the software. So as you can see, the probe mismatch has worked a treat here, because it recognized, starting the scope from where we left off, we'd actually got a red ×1 test lead connected. We now have a BNC Plus pressure transducer. So we'll say run with found probes. So there's a nice little warning there to stop you making a measurement error. All right, remove the zoom. We've got to make some amendments. So now we want the maximum pressure range for our transducer. We can turn off filtering here, only because the more features we have active during streaming, we'll have a little bit of delay when we're trying to look at the data in the decode table. So first things first, let's get LIN Bus active. So ignition on, there is LIN Bus. In fact, if I go to views and reset, okay, that removes that sort of block of yellow data, which was a scaled up current clamp. And in our decode table, we want to add the filter. Remember, we went for frame identifier contains 24. And there we have just the air conditioning pressure switch, which we've confirmed is the ID, frame ID for that node for that ECU. All right, so what is there of interest here? It's actually the pressure value. So I'm going to pause, and we'll just pull a time ruler out, and we'll ask for channel B mean value between the time rulers. and it's coming up with 28.76 millibar. Well, it would do because I haven't plugged it in. So there's a user error straight away. Okay, there we are. And we're looking for stable value. So we'll pause that, and there we have it. The mean value, let's just check, between the time rulers is 4.929 bar. So let's write it down, 4.929 bar. And more importantly, in the decode table, if we modify it so that we're only decoding between the time rulers, we'll only get the bytes of interest, and we have 4 in total. So look at the data field there. We have 76, F9, 2F, 52. We know that's hex because of the letters. Now within there, those bytes, or some of those bytes, maybe only one, will represent air conditioning pressure. So what we need to do now is change the state, increase the pressure, decrease, whatever it may be, and look at which bytes change in the data field. So it's probably best at this point if we modify the decoder again, and we'll turn off between the time rulers. So now we'll decode across the entire buffer. Run PicoScope. Let's close the rulers, and we'll switch on air conditioning. So we'll go to ready mode. So ready mode is on, air conditioning is on, and we should be seeing an increase in pressure. We're seeing it climb up there. If I just bring this down a little bit, we can see there that our pressure is now at 7 bar and quite stable as well, climbing still. A tip here then, we want to get a portion of pressure where there is no change. So if we've got ripples in our pressure, if we now turn the air conditioning off, so ignition is now off, and we'll see that falling steadily. But I'm sure within there, we had a transition from our 4.929 bar, and we had a stable pressure value. I think it was here. I think it's probably safe to say that between those 2 points, our pressure was stable. If we modify the decoder, so we now decode between the time rulers, we've only got 4 bytes of interest there, or sorry, 4 packets of interest at this stage. And our measurement, we have, right, so we have a pressure value of 7.043 bar. And let's just grab this viewport so we can keep that in view, and then flick over to the decoder. Let's drag this up a little bit. Right, so what has changed? So we can see that before we had 5E, F9, 2F, 52. Now our pressure's changed. We can see that the first byte has gone to FC, F9 to F52. So it looks to me as though byte 1 is is indicating our refrigerant pressure. And let's see if we can prove that. We'll run PicoScope again, and let's just see which byte is changing. Well, what we'll do first of all is go back to decode between time rulers off. So we'll decode across the entire packet, take the ruler away, and then power up again. So we go to ready mode. Air conditioning is on. Run PicoScope, and we should see that pressure starting to change. Note the first byte in this column here. In fact, if let me pull this up here. Try again. Let's put it up here. There we are. Let's close the viewport and scroll along. We know we are only interested in our protected identifier, frame ID. And if I pull a ruler in here as well, we should be able to see transitions in pressure. Yeah, and the only byte that's changing is that first byte. Oh no, actually the second byte has now moved. So now that's gone to FA. Nevertheless, it would appear that our pressure is directly proportional to that first byte. So food for thought when you're actually doing this, be aware that 2 bytes could be used to denote air conditioning pressure. But we've gone back to F9 again, which is interesting because when it fell, it was F9 in the second byte. But we'll work with that. And then from that, we'll see, based on those 2 points that we've obtained, whether we can then apply a scale and offset and work out what those pressures are. Here we have our air conditioning pressure, and I've deliberately chosen 2 buffers from that previous capture. So if you look at buffer number 1, we've got, well, let's pull the ruler down. I'm looking for a good transition in pressure. So 7.3 bar as an average. And notice in the decode table, 16 FA, so those 2 bytes there, I think are representing pressure. We go to buffer 2, and then we look, as we drop down our pressure, we've got FA, but then as we come down, we go back to F9, which was typically what we saw before, when we thought just the first byte was changing. So as it would seem, certainly pressures round about the 6 bar or heading towards 6 bar utilize the first byte, but then when you get above that, well, let's see if we can work this out, where we get the change. So where does F9 become FA? There it is. If we double click and then we move the ruler, so it would appear we move over at 7.112 bar. Okay, so again, what does all this mean? Where is it heading? Let's export the decode table. So we click export, and I've done that already here, but that is going to export all buffers. Now, I haven't shown you this, but we can flick between just decoding the current buffer. Notice we lose that column there. That's just this buffer, or all buffers, which means we're going to decode buffers 1 and buffer 2. Okay, so let's bring in the decoder table, and here it is. So this is our decoded data exported from this PS data file, and here is the file of interest. So we've missed a trick here. What I could have done was use the index feature. With that said, we can't export, but let me show you the index feature anyway, because we will be able to do this very soon. Okay, so we'll add another filter. This one is called indexing, and we go for data and index of, that's what we're after. And we are interested in these first 2 bytes. So if we were to count, starting from here to the left of byte 1, number 1, that would be 1, 2, 3, 4, 5. So I think we write this as 1-5 and then add. And we'll see there that I've got that completely wrong. It may be that we've got to count 0. So that first point before 1 of byte 1, number 1 of byte 1, is actually position 0. So let's edit that and type a 0 in here. And there we are. So the plan would be, going forward, that we would export this and it would include this filtered data. We can't do that at the moment. The filtered data doesn't export. Nevertheless, we can work with Excel on that. First thing to do here then is to copy the data. So let's move it to another column and let's put it over here. And now we're going to use some magic, thanks to my brother from another mother, Ben Martins, the master of everything Excel. that's shown me how to single these bytes out so that we can work with those bytes and then convert them over. Okay, before we do any more alterations to this sheet, always save your file as a Excel SX workbook. Okay, just because we want to be sure that we save the formulas. If we're working with CSV and add formulas and then save, we will lose the formulas. Right, so to extract the bytes of interest, we type in the equal sign, and I've already written the formula out here. It is concatenate, open brackets, comma, mid, the cell of interest, starting at position 5, I'll explain why shortly, for 1 character, then comma, mid again, O2, cell of interest, this time starting at position 1 for 2 characters. So you'll see in a second that what we're doing there is we're swapping hex values around. Why is that? Well, Pico has displayed the hex bytes as most significant byte first, which is typically how you do conversions when you go from binary to hexadecimal. However, the LIN protocol works with little endianness, so least significant byte first. So really what should have happened there would be FBF9 became F9FB. Now that would have been a 16-bit value, so there'd have been 16 bits in those 2 bytes. We only need 12-bit. This is a 12-bit sensor. And you noted that during the video that F never changed in the second byte. It was simply 9 went from 9 to A, and byte 1 was constantly changing. So we reorder this to least significant byte first, and we take away the F from the second byte. We end up with a 12-bit hex value 9FB, which we then convert to decimal. I'll just give this a title. This is going to be called byte 0 and byte 1 as least significant byte. LS byte. Let's keep it like that. Now then, what we next do is change this to, oh actually no, before we do any more, let's double click that. So that applies to every cell. We've extracted the desired hex values from the data field. We'll now convert them into what we call the raw decimal value. And to do that, we need to go from equals hex to dec. And the cell of interest, close brackets, and we end up at 255. Double click in here. That will apply that to all data. Now this is interesting. This column here, column 41, that's come back as a 0, and it looks like it was on the cusp of going from buffer 1 to buffer 2. So we probably had half a packet there. So we will just delete that row because that doesn't really make any odds. Just stops us having a crazy value in the graph. Well, once again, I've shot myself in the foot by saving just 2 buffers of the previous capture in the video. Not to worry, because we can still apply the values that we obtained in the video earlier. That was 76 and F9 for 4.929 bar, and an FC F9 for 7.043 bar. I'll just draw a text box in here so we can actually see our workings out and how this has come about. So remember, 76 F9 was equal to 4.929 bar. Now that is most significant byte first. We need to flip that around to F9 76. We need to flip that again. Well, not so much flip. We need to remove this F here. This F never changed. That's a 16-bit hex value. We only want a 12-bit value. All we need from that is 976. So then we want to change 976 into decimal. And to do that, we use the Windows calculator. Make sure it's set to programmer. Type in hex and 976 in decimal. 2422 is what we call our raw decimal value that equates to 4.929 bar. Let's repeat this again now for the other value. Remember, we had FC, F9, and that was equal to 7.043 bar. Now that was most significant byte first. We want to go change that to F9 FC. That's a 16-bit value. The F we're not interested in, so that becomes 9FC. 9FC in hex. 9FC converts to 2556. So decimal 2556. Again, that's the raw decimal value, which equates to 7.043 bar. And then from that, we can place that into our spreadsheet, thanks to Ollie Hayward. I've actually got this on the forum for something else, but we can use it here, and I will add it to another forum post, which is for LIN Bus. Let me see if I can move this over so as we get this values that we've just calculated. So raw decimal value of 2422 equals the final value of 4.929 bar. The second value that we had was 2556, which gives us a pressure value of 7.043. Okay, and there is now our scale and offset values. So if we multiply our raw value by 0.015776119 and add plus the scale, which is a minus value, note that minus value, we'll end up with the pressure value. So we'll put this now into Excel over here. So this would now be pressure in bar. So let's apply our scale and offset into here. So this would be equals, and this would be cell of interest Q2, raw multiplied by scale. Our scale is 0.015776119, close brackets, plus our offset. Let's put that in brackets. Our offset is minus 33.280.76119, close brackets, equals. So that value there is equal to 7.027 bar. So let's just double click on here. So that applies to the whole formula, and you see there that pretty much in those two buffers we were at 6 bar, 6.7 going up to 7.4. We can now graph that. So if we click here, insert, and there's our pressure value going down, and then it does shoot back up there. So I need to find out why that was, because we went from 7 down to 6.8 and then it jumped back up to 7.4. That's round about line 40. Let's have a look at that. Yeah, it does represent the pressure there. And let's see where that occurred. Let's increase the size of roundabout buffer. Okay. Oh, what might have happened here? I need to check on this, but it looks as though when I saved the buffers, I chose 2 buffers of interest that didn't actually correlate. So in other words, it wasn't buffer 1 and 2. I may have saved buffers 1 and 5, which is why we've got that abrupt value or abrupt jump in pressure, because that would not be consistent with what happened. All right, so let me pull this down and hopefully summarize. We started with raw data here, FB, F9. We know that those 2 bytes change in relation to pressure, and we correlated those 2 bytes with pressure using a pressure transducer. Those 2 bytes are in most significant byte order, and 2 bytes represent 16 bits. We need to change them to a least significant byte, so a little NDNS, and that is simply converting FBF9 to F9FB. We know that the second F of byte 1, because this is byte 0, this is byte 1, that never changed, so we dropped that to 9FB. That gave us our 12 bits of interest. Those converted into raw decimal value is hex to dec, which is 255. We then applied the scale and offset that we calculated from our spreadsheet here, where our scaling was this value plus the offset. Remember, it's a minus offset. All we had to do was enter in these values, the raw decimal and the actual value, and the spreadsheet delivers the scale and offset. We applied that to these values here, and happy days, we've got pressure values. So we've now managed to convert the 2 bytes of interest here into true pressure values. All right, so the proof, as they say, is in the pudding. So I've now opened the original capture. Remember, original capture had 15 buffers in there, and I unfortunately took 2 buffers of interest, not thinking about making sure the buffers followed one another. But let's just choose somewhere quite random on here, and let's choose, okay, that's interesting. Let's go for add our filter. We know the frame identifier contains 24, and let's go for this value here, so dBF9. Well, let's run through that as we would using the calculator. So first of all, we now know that dBF9 has to be swapped round, and we lose the F, so that will become hex 9 dB. And in decimal, that is 2523. So let's remember that. Copy. Go back to the standard calculator. Let's paste that in there. Control V. So 2523 multiplied by our scale. So if we multiply this by 0.015776119, that is equal to 39.8. Then we want to add our offset, it's raw times scale plus offset, and that was 33.280 76119. 280.76119. That is a minus value, is equal to 6.522 bar. Well, let's prove that. So dBF9, let's double click on that, and let's pull out some rulers here and ask the software to give us the pressure value. Well, first of all, let's go to serial decoding. Cancel. Sorry, let's go to the serial decoder here and modify it so that we decode between the time rulers. Finish. So there we have dBF9, just that packet of data there. And we'll ask for the measurement between the time rulers. So B, the mean value between the rulers, we've got 6.528, and in our calculator at 6.522. Okay, so thanks for hanging on in there, but there we have converting raw hex values from the data field in LIN into pressure values.